An assertion from educator Carlos Plain. In Durham, I've committed my entire calling to enabling an unequivocal speculation about the universe. But that point this takes place, the speculation is being watched out for. I embrace this test because it is through such looking that we advance and gain ground in science. The James Webb Space Telescope is basically disturbing some extensively held convictions in cosmology that have been seen as truth for quite some time. One more ultra-tracking image has revealed that we have committed blunders in space science. The telescope, which was intended to uncover the focal stars of the universe, is truly groundbreaking. The previous viewpoint could introduce a completely new legitimate perspective. Not all experts are dismayed by these new revelations. Various specialists are welcoming these levels of advancement, since it has long been evident that there were issues with our previous hypothesis. The peculiarities in viewing the universe's rate of expansion alone should have raised concerns among experts a long time ago. Instead of definitively addressing these alarms, many adhered to outdated speculations. The cosmic microwave background radiation CMBB, which is the oldest light in the universe, was formed around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. This chain reaction, known as ionization, made the universe transparent to light. The CMBB was first recognized in 1964 by American physicists Arnold Penzias and Robert Wilson. While they were managing new radio detection technology, they encountered a consistent clatter coming from every direction. This discovery was initially considered solid evidence for the Big Bang theory. Penzias and Wilson were awarded the Nobel Prize, and their revelations became a critical foundation in the history of space research. The CMBB indeed provides a brief glimpse into the early universe, with minute temperature variations offering key data about the conditions shortly after the Big Bang. Analysts used the CMBB as a dependable marker to measure vast portions of the material universe, including the rate of its expansion. Edwin Hubble had previously made such assessments in the late 1920s. It observed that faraway massive galaxies were moving away from us in every direction, and that their speed was associated with their distance. A relationship now known as the Hubble law, or the Hubble constant. Despite the fact that Hubble's measurements were not as precise as those of today, they were critical at the time. When the CMBB was later discovered, experts recalculated the expansion rate, finding it significantly lower than Hubble's initial calculations. Subsequent recalculations using Type Ia supernova as standard candles provided more accurate measurements. However, discrepancies remained, and the difference in expansion rate calculations has been known since the 1990s. Experts have speculated that there may be issues with the CMB data analysis techniques, or perhaps with our understanding of cosmic evolution. Discrepancy known as the S8 tension or Hubble tension suggests that our interpretation of the universe may be fundamentally flawed. Since the James Webb Space Telescope JWST began operations, it has produced impressive data that may help address this issue. Galaxies so old and mature that their formation might theoretically have begun before the Big Bang are now challenging old scientific theories. Space science currently faces what is considered the greatest crisis in modern cosmology. The universe's rate of expansion and theories about its origins are under intense scrutiny. New images reveal a universe that differs drastically from previous models. This tension has served as an early warning for professionals still clinging to outdated theories, now grappling with the realization that our understanding may be incomplete. This uncertainty has left many scientists troubled and disheartened. To address this crisis, we must understand how science functions. Theoretical scientists use a blend of mathematical models, observational data, and logical reasoning to arrive at conclusions. Their insight comes from identifying anomalies in test results and theoretical investigations. Theory itself implies advancements and evolving ideas rather than absolute truths. Our understanding comes from images provided by telescopes, sound waves, and radiation captured by radio telescopes, as well as data from neutrino and gravitational wave detectors. The JWST allows us to break down the oldest light into individual frequencies and examine it in remarkable. It can reveal which elements were present in galaxies billions of years ago, the mass they contained, and how many stars they hosted. However, Webb's images also have limitations. For example, it can't always distinguish galaxies or black holes that appear similarly bright due to gravitational lensing. Our understanding has evolved to include multiple possible outcomes, often dismissing alternative explanations. New findings from the JWST offer critical clues that may replace outdated theories with new insights. Researchers are now confronting these revelations, which seem so extraordinary that finding new explanations is proving difficult. These discoveries are shaking the foundations of physical science, causing concern among many experts. Current scientific principles are still deeply influenced by the work of Isaac Newton. For a very long time, his laws of motion and gravity formed the basis of our understanding of reality. Newton's laws work remarkably well under typical Earth conditions. However, in space, his concepts required significant expansion accomplished by Albert Einstein in the 20th century. Einstein's special theory of relativity, published in 1905, changed how we perceive reality, showing that the laws of physics are the same for all non-accelerating observers. His general theory of relativity, published in 1915, extended these ideas with mathematical formulations describing how mass and energy warp spacetime idiosyncrasies, considering the bend of spacetime achieved by masses like stars or universes. While Einstein's theories were clear in various regions, he saw their boundaries and sought a binding, unifying structure. Without progress, no scientists have yet accomplished this. It is fascinating to consider where the mistakes could lie. A prominent American astrophysicist, proposed that solving this issue could lead to a Nobel Prize. We truly need to explore what reality might have been, confused whether there have been misinterpretations of idiosyncrasies, or if telescopes themselves might be to blame. Dark matter and dark energy are prominent individuals in the cosmological crisis. Current models suggest that dark matter and dark energy together account for around 95% of the universe. Neither has been clearly seen or demonstrated to exist. They may not exist by any means, or perhaps have properties we don't yet understand. One chance being inspected is that the properties of dark matter might have evolved over time, potentially showing some kind of insight into gravity, which should bring about mass interaction or spacetime. Gravity has not been definitively shown to act exactly as expected. In any case, the reality of Einstein's idea for a spacetime twist has been supported several times. It can't completely block the credibility that gravity possesses remarkable properties, or that some other effect is causing gravitational interaction over the explicit properties in cosmology and space science have spread throughout as central constants recognized as reliable, generally due to their consistency. assessments indicated that the assortments in these constants could offer new pieces of information into the universe, potentially grasping idiosyncrasies without dark energy. It is also possible that our understandings of light movements have been off, leading to mistaken distance assessments and grandiose framework ages. Perhaps our assumptions about the universe's conditions were imperfect, or we misread the cosmic microwave background radiation. It could attempt to be simply that the universe doesn't originate from a single initial stage of testing, the speculation of the big but little bungles in the Webb telescope or other observational devices can't be ruled out. Some subject matter experts and scientists recognize that mistakes in instrumentation, data handling, or understanding are generally possible. The persistent reassessment of cosmological hypotheses highlights the principal nature of legitimate advancement, the ability to change and move our understanding based on new evidence. The James Webb Space Telescope's observations are more than an innovative leap. They represent an enormous moment in our journey to decipher the mysteries of insider secrets. As we wrestle with these revelations, it is key to see the broader context and the consequences of such reliable changes in the area of cosmology. The methodology involved is often driven by the need to refine hypotheses in alignment with new insights, the discovery of exceptional anomalies or abnormalities in unsettling established hypotheses, however, also presents a critical opportunity for legitimate development. Hypothetical models in cosmology are made to provide a clear structure for understanding the universe's origins, progression, and advancement. However, as new data emerges, these models should be tested and, if necessary, rethought to accommodate new insights. One critical area of focus is the nature of dark matter and dark energy, which are central to contemporary cosmological models. Dark matter, a subtle type of matter that doesn't emit or absorb light, was proposed to account for irregularities between the observed rotations of the galaxy and the mass expected by recognizable matter alone. Dark energy was introduced to address the observed accelerated expansion of the universe. At any rate, despite their fundamental positions in current models, both dark matter and dark energy remain intriguing, with investigations on Earth having until now failed to indisputably identify them. This has led researchers to explore alternative hypotheses and possible explanations. The trial of grasping dark matter and dark energy is heightened by the vast scale associated with cosmological studies and the observation of distant universes. The cosmic microwave background radiation, along with other remarkable features, provides indirect evidence of these components. Yet their elusive nature remains subtle. Uncertainty has prompted analysts to consider a range of hypotheses, from modifications to existing models to entirely new laws of physics. Some theories suggest that dark matter could be made of more intriguing particles than previously thought, or that dark energy could represent a new fundamental force. Another captivating area of investigation is cosmological investigation of cosmic inflation. This theory proposes that the universe underwent rapid expansion in its earliest moments, leading to the vast scale structure we observe today. But inflationary theory has successfully explained various features of the universe, like its homogeneity and flatness. It also raises concerns regarding the nature of the inflationary period itself. Observations that challenge established models of inflation could lead to revisions in how we interpret the universe's early history. Finally, the search for extraterrestrial life remains a principal driving force in space exploration. the discovery of exoplanets, planets outside our solar system that orbit stars, has opened new avenues for studying the conditions necessary for the development of life. Advances in telescopes, for example, the James Webb Space Telescope, enable us to explore the conditions of these exoplanets for potential biomarkers. The possibility of finding life beyond Earth holds profound implications for how we might interpret the universe and our place within it. Conclusion: the reevaluation of cosmological theories is a testament to the strength of the scientific method. The James Webb Space Telescope and other advanced instruments have provided astonishing insights into the universe, prompting researchers to revisit and refine old theories. This process of continuous inquiry and correction is vital for advancing our understanding of the universe and addressing the fundamental questions that lie at the core of cosmology and space science. As we continue to explore the universe, we remain engaged in a quest for knowledge that not only seeks to answer key questions but also inspires future generations to push the boundaries of human understanding.